Hi everyone. Today we are in section 1.7, which is called Introduction to Limits and Continuity. Now this is the first of 3 sections in a row that we'll talk about that involve the topic of limits. They are 3 fairly short sections, but they give us a lot of information about this concept, and this concept is really the foundation on which all of the rest of calculus is built. So it's important that we understand the idea of limits, how they work, and some of the basic ways to calculate them before we get into section 2.1, which is the beginning of the real calculus that we're going to do. Okay, so all of calculus, like I said, is built on the concept of a limit. Now, when you're asking about limits, you're really asking a very simple question about a function. You're asking, how does a function behave, meaning what does it do, as you get closer and closer to a point? So that's a very simple question. You pick some point and you say, as I get closer and closer, what does the function do? And it turns out functions can do some really interesting things. So let's start with a slightly different notion called continuity. This is probably something that you've heard about in a previous math class, but we're going to define it again here. Given some function, we say that it's continuous at a certain point, continuous at a point, if 2 things are true. Number 1, it has to actually exist at that point, meaning the point has to be in the domain. If the function doesn't exist at the point, like because you divide by 0 or take the square root of a negative number or something, then it's definitely not continuous. So it has to exist. But also, there has to be no jumps or breaks at that point in the graph. And I'll show you some examples in a second, but these are the 2 conditions. It has to exist, and then at that point, it has to be, you can think about this as it has to be smooth. It can't do something crazy. And then we say that a function is continuous in some whole interval if it's continuous at all of the points in that interval. So let's look at a couple of examples. Over here on the left, this green function looks like it could be some kind of polynomial, maybe some kind of x cubed function or x to the 5th or something like that. At all of the points in the domain, it exists, right? We don't see any holes here. And it's smooth. There's no jumps, there's no breaks, there's no asymptotes. So this function, just by the picture of the graph, is continuous everywhere. It's continuous at every point. Here's another function. This one looks like it could be maybe 1 over x or something like that. And so there's one particular point where this function is not continuous. This function is not continuous at x equals 0. Because at x equals 0, something crazy happens. It's not smooth. It goes from looking like all the way down to negative infinity to jumping up to positive infinity. And that's not a very smooth thing to do. So this function is continuous at all points except at x equals 0. Here's one more. This function is what we call a step function. What that means is that it's horizontal. In this case, it's this constant value all the way to negative infinity. But then at this x value, it jumps from this value, whatever it is, maybe negative 2, up to negative 1. And then it's negative 1 for a while, and then it jumps up to, say, 1, and then maybe 3, and then stays there forever. Now, when you see the solid dot, what this means is that at this exact x value, let's call this, let's just say that that's negative 1, and this is a height of negative 1, and this is a height of plus 1, just to have some concrete numbers there. The fact that it's a solid versus an open means that at f of negative 1, I have to say which value is it. Is it the lower one or the upper one? And the solid tells you which one it is. So at negative 1, the value is negative 1. But if I go the smallest teeny tiny amount to the right, maybe 1 over a trillion just to the right, then the value jumps up to 1. So this has jumps or breaks. So that means this function here is not continuous at this x value, at this x value, and at this x value. It's continuous everywhere else. So for example, if you looked at this interval of x values in the middle, you could say that the function is continuous on this interval. There's no jumps or breaks on this interval. But it's discontinuous, which is another way of saying not continuous, at those 3 points. Another way that we could phrase this, and I'm trying to lead us from continuity into the idea of limits, another way to say that f of x is continuous at some particular x value, x equals c, is to say it like this. The y values of f of x, when x gets very close to c, are very close to f of c. Okay, so that's a little bit of a roundabout way to say it, but I want you to really, if you need to, pause the video for a minute and think about what that says, because this idea is really, really important. This says that as x gets really close to c, the corresponding y values get really close to f of c. So put one more way, as x approaches c, f of x approaches f of c. So this is another way to think about continuity. Here's an example of a function. Suppose that you've got this function over here. At the value x equals c, the function is this number here. Maybe that's -1 or whatever. But everywhere else, the function is on this nice little weird curve. But at x equals c, it jumps down and then jumps back up and keeps going. So this is not continuous at x equals c, because let's remember what we just wrote on the last slide. We said continuous kind of means as your x values get closer to c, I'm using this arrow now to mean approaches, as x approaches c, the y values, that means f of x, approaches f of c. But that's not true in this picture, because this is f of c, but as x is close to c, so if you ignore the actual circle here, but you look near here on one side or near here on the other, these are the f of x values when x is close to c. So you've got this big disconnect or discontinuity here. As your x values get closer and closer, it looks like the value should be right here, but it's not. It's actually down here. And so that violates our continuity definition. Now, a lot of the functions that we've seen so far are continuous. In fact, when we say are continuous, we mean are continuous everywhere. For example, exponential functions. The domain of an exponential function is all real numbers, and it's continuous at all real numbers. Same with polynomials. Same with sine and cosine. So these three functions are continuous everywhere. Now, another property of a function is that it might not be continuous everywhere because it might not exist at some places, like that function of 1 over x went down to -infinity and then jumped up to +infinity, so it didn't exist at 0. But that function had the property that everywhere it did exist, it was continuous. So another way to say that is a function that's continuous on its domain. Everywhere it exists, it's continuous. And we've seen some other ones like that. For example, logarithms, they don't exist everywhere. They don't exist at 0 or at negative numbers. But everywhere they do exist, they're continuous. Same with the tangent function. Tangent had a bunch of vertical asymptotes, but in the middle kind of looked like this and repeated over and over again. Everywhere that exists, it's continuous. And same with rational functions, like 1 over x. Now, up here, let's think about this one. This is not continuous everywhere. We already said that because it's not continuous at c. But also, we can't say that it's continuous on its domain. That's also false here because x equals c is part of its domain. It exists. It's right there, but it's not continuous there. So these are kind of extra nice compared to ones like this. These are continuous everywhere, and these are continuous everywhere they exist. Okay, now we're going to move from continuity into limits. Now, first, the way we write a limit is this kind of crazy notation. So let me break this down for you. We've got three parts, really. We've got the word LIM. LIM stands for limit. We've got a part below it that tells us the x values that we care about. And then we have a function that we're taking the limit of. So three parts. The way that we read this is that it's the limit of, that's this part, the limit of f of x, that's this part, as x approaches c. That's this third part. So the limit of f of x as x approaches c. And all we're really asking here is a very similar question to the one that we asked about continuity. What does it look like f of c should be, not asking what it is, what does it look like it should be if you, number one, ignore f of c itself, it might not exist. But if it does, ignore it completely and look instead only at the x values near it. Okay, so let me repeat that. This is the book doesn't phrase it this way because it's a little informal, but this is the absolute best definition, in my opinion, to keep in your head when you're thinking about limits. The limit of a function as an x value gets closer to c is asking, what does it look like f of c should equal if all you're thinking about is the values of f nearby? So you might have this function, and f of c is right here, and you want to say, ignore that point, and just look at all the x values right to the left and the right. Based on those values nearby, what does it look like the value should be? That's all a limit is. Now we're going to see a bunch of examples. Here's a function that is kind of interesting to think about. Sine of x, we know about sine of x, divided by x. So sine, you remember from 1.5, looks kind of like this and just repeats over and over again, reaching always a height of 1 and a negative 1 on the bottom. But now as we divide by x, that's a little bit weird because that means as we go further out, instead of going long like this, you're going to get kind of shorter and shorter because you're dividing by that x. And so the question that we're going to ask now, this function definitely does not exist at 0, right? If you try to plug in f of 0, you have a problem. You get sine of 0 over x. Okay, well, sine of 0 over 0, and you have to think, well, okay, sine of 0, I never remember whether sine of 0 is 1 or cosine of 0 is 1, but I know that one of them is. And the way I always think is, I remember in my unit circle, cosine tells me the x value. So at an angle of 0 in my unit circle, I'm at the point here on the circle. This is an x value of 1 and a y value of 0. So that means cosine of 0 is 1, sine of 0 is 0. That's how I always remember. So this is like 0 over 0. And that gives us a problem. We want to know what should it be. It obviously doesn't exist. But it's kind of like asking this question. If it did exist, what would it be? And so if you plug this function, sine of x over x, into your graphing calculator, into Wolfram Alpha, into something like that, this is the graph that you get. And it's pretty interesting. So here at pi, for example, it's 0. That's because sine of pi is 0, so you have 0 over pi. And it gets, if you were to keep going, it kind of shrinks closer and closer to the axis, and same thing over here. But in between, it goes up to 1, has a gap there. Why does it have a gap? Because it doesn't exist at 0, and then it keeps going. So based on the picture, what should f of 0 be? If we ignore the point itself, ignore it, and you just look nearby, what does it look like it should be? It looks like it should be 1. And that's the answer. So a limit says, what should the function be? The limit of the function as x goes to 0. So we ignore f of 0. In this case, it didn't exist. But even if it did exist, we ignore it. And we just look at x values nearby. And we say, based on that, what should it be? And it looks like it should be 1. Now, this is not a very technical definition, but we will get more technical. This is the intuition that you should always keep in your head when you're thinking about limits, though. Here's another example. This function f of x looks almost exactly like a line. At height 1, or sorry, at x value 1, it has height 5, and it goes through the origin. So this is almost, it's not, but it's almost y equals 5x. The only difference is that at 1, it doesn't equal 5. It equals 10. So this is a weird kind of function, right? It exists everywhere. The domain is all real numbers because it has a y value everywhere. But at this one, it's obviously not continuous because it has a jump. So not continuous at x equals 1. But here's what we're going to ask. What is the limit as x approaches 1? What is the limit of this function as x gets really close to 1? So remember our kind of informal definition. That says, what does it look like f of 1 should be if you ignore what it actually is? In this case, it's 10. But forget about that. Ignore x equals 1 and just look at the x values near it. What does it look like it should be? It looks like it should be 5. So the limit is 5. This is a key point I want to repeat one more time. When you're taking the limit as x approaches 1, the limit here as x approaches 1, we do not care at all, what actually happens at 1. In this case, it's 10. We don't care if it's 10 or 5 or negative a trillion or if it's nothing at all. We don't care what actually happens at 1. We ignore it, and we just look what happens near 1. Okay, here's another slightly trickier example. Here's a function that looks like two lines that we've kind of split. So this looks like maybe it's 5x like the other one. This is some other line. And we're kind of joining them together to make a new function. Our new function is this first line for a bunch of x values until we hit 1. At 1, we jump up to this other line for the rest of the x values. At f of 1, the actual value is 10. Remember, that's what the solid line means. The actual value is 10. And we do the little hollow dot there to indicate that we've got this jump. So f of 1 equals 10. And just like the last one, this is not continuous. I'm going to use CNS to abbreviate continuous at x equals 1. But what should f of 1 be? When we say, what should f of 1 be, that means we're really saying what is the limit as x approaches 1 of our function f of x. Okay, so let's think let's think of our informal definition again. The question is, if we ignore the actual value at 1, ignore it, and look only at the x values nearby, what does it look like it should be? And the answer is that it's ambiguous. It doesn't look like it should be any one thing. On one side, it looks like it should be 5. On the other side, it looks like it should be 10. Okay, well, that's not a very satisfying answer because you have to pick one, and you can't just pick 7.5 in the middle. One side makes it look like it should be 5. The other side makes it look like it should be 10, and that's ambiguous. So this is an example of where the limit does not exist. If you can't answer the question, what should it be, then the limit doesn't exist. And that's a perfectly fine answer. Some limits, like this one right here, like this one right here, just don't exist. Let me repeat one more time. Because looking at it from the left makes it look like it should be 5. Looking from the right makes it look like it should be 10. And that means the limit doesn't exist. Now let me jump back to continuity now, because the real definition of continuous comes from a limit. And we couldn't say that before because we did continuity and then we did limits, but now we can jump back to continuity and give the real definition. So here's the real definition. The function f of x is continuous at the point C if two things are true. This first one is the same condition we said before. It has to actually exist at the point. The second one is that if you look at the limit of the function as you approach the point, you get what it actually is. So now we can phrase that in terms of our informal definition of a limit, and hopefully it makes some sense. This says the value at x equals c is exactly equal to, so the value at x equals c is exactly equal to what the nearby points suggest it should be. So discontinuity would be or one example would be the nearby points suggest that the value should be this, but it's actually this. Or the nearby points don't suggest anything because there's a jump. So continuity at a point means that the function exists and its value is what it should be. Nothing crazy happens. So I'm going to state now an important theorem in calculus. We're not going to use it in this section. It's not going to come up until later, but this is a good place to mention it. This is really one of the fundamental theorems that you learn in calculus. Now, it's a fancy way of saying a fact that should be really, really obvious to you. The intermediate value theorem says, suppose that you have a continuous function on some interval of numbers. So between a and b, you've got a continuous function. And here's a little picture here. Between a and b, we have a continuous function. It goes up and down and up and whatever. Then for any number k between f of a and f of b, so here's the height of the starting point f of a, the height of the ending point f of b, and for any k value in the middle, for any k, there's some point c in our interval of x values that actually hits that height. Okay, so let me show you in the picture what that means. That says I can pick any height between f of a and f of b. We'll call that k. And that means at some x value between when I started and when I end, I must have actually hit that height. So we can draw a horizontal line. And at some point between a and b, I will actually hit my graph at least once. So here I hit it here. That means we can call that C. Now this should be super obvious. Here's an example of using this fact in real life. And if I just told you this fact independent of the phrasing it like the intermediate value theorem, you would say, duh, of course that's true. If you had a drink, if you had a soda that was at room temperature, maybe 70 degrees, and then you put it in the fridge, and you take it out an hour later, and now it's 30 degrees, then at some point in the middle, starting at 70 and ending at 30, it must have been exactly 40 degrees. That's because temperature is continuous. It's not going to jump up or down. So if you started at 70, ended at 30, then at some point it must have been 40 degrees. If you start and your car is at 0 miles per hour, and then you accelerate to 50 miles an hour, at some point you were going exactly 27.3 miles per hour. So that's just common sense. But in order for that to be true, your function has to be continuous. So that's how this comes into play here. Now we're going to see a lot of different ways to calculate limits, especially in 1.8 and 1.9. And the way we do that depends on the function. So I'll just mention a couple of easy ways to calculate limits in easy situations. If you have the graph, well then you just look at the graph like we've been doing all section. But sometimes you have a formula. So let's look at this limit for a second. Suppose that we've got the limit of f of x as x approaches c. And suppose that limit, we want to know what it is. We'll call it L, but we want to know what it is. One of the easiest ways is if you know that your function is continuous at that point. Remember, we know lots of continuous functions like exponentials and polynomials, and we know lots of things that are continuous on their domain, like logarithms. If it's continuous at that point, then the limit is just whatever it is. And that's because the definition of continuous. Continuous means the limit is what it should be. So one way to calculate a limit is to say, is my function continuous? And if so, just plug in c. That one's easy. Sometimes we can do some algebra, and we'll see more of this in the next section, but here's an example. Consider the limit as x approaches 3 of this rational function. Now this looks like it can be factored, and we are going to factor it. You may remember this is what's called a difference of squares. So this can be factored as x plus 3 times x minus 3. And if you're unsure about that, multiply that back out. You'll get an x squared, then you'll get a plus 3x and a minus 3x that cancel, and a minus 9. Now what's interesting is that over here we couldn't plug in 3 because we got 0 over 0. But here, that x minus 3 on the bottom, which was causing problems, is going to cancel with the x minus 3 on top. But here's something that a lot of times in pre-calc or algebra, you always skip over this part. If you're going to cancel an x minus 3, then you have to add the caveat that the result, when you cancel, you get this. This is true for all x values other than 3. It's not true at 3, because at 3, this is undefined, and this is 6. So this is true for all values that are not 3. But here's the key. When we're finding a limit, we don't care what actually happens at that point. So if we want to find the limit as x approaches 3, then we're allowed to make this equality because it's true everywhere but 3, and we don't care what happens at 3 because that's where we're taking the limit. So this function looks like one of the ones we saw before, a line with a hole. So for the limit, we say ignore that point and look at the x values nearby. And the graph says it should be 6. And if we look, we can cancel, just like, because we factored here, we can cancel that x minus 3, and what we're left with is the limit of x plus 3 as x approaches 3. And now, this is just a polynomial. So it's continuous, so you can just plug in 3, and you get 6. And that's what our picture says. So 2 ways that we know to do a limit. Well, 3 ways, really. One is if you have the graph, look at the graph. Number 2 is if the thing you're taking the limit of is continuous, just plug it in. And number 3 is if you have a rational function, try to factor and cancel, which you can do as long as the point that you're canceling at, in this case 3, is the thing you're taking the limit of. Okay, so in 1.8, we'll see a lot more examples of ways to calculate limits and a little bit extra in 1.9. And then finally, by section 2.1, we'll be talking about derivatives and real calculus.